What if I told you that one of the most fundamental forces in the universe is also one of the least understood? It dictates everything, from the tiniest molecular collisions to massive planet-sized storms. It's been at work since the very beginning of time, shaping the universe, guiding its evolution, and inevitably sealing its fate. It might even control the direction of time itself. And it could be the very reason that life exists at all. Let's start with a simple question. How much energy does the Earth radiate into space? I mean, it's visible from space, so it must radiate a lot of energy in form of light. But the Earth absorbs an incredible amount of energy from the Sun every day. So how much of that energy does the Earth actually send back? Is it 20%? Maybe 70%? Or all of it? It turns out, in the grand scheme of things, the Earth actually radiates back the same amount of energy that it gets. Earth receives approximately 340 watts per square meter of solar radiation at the top of its atmosphere. Of this incoming energy, about 30% is reflected back into space by clouds, atmospheric particles, and the Earth's surface, while the remaining 70% is absorbed by the atmosphere and the surface. To maintain energy balance, Earth emits this absorbed energy back into space as long-wave infrared radiation. Because if it didn't, well, the planet would keep heating up indefinitely. And unless you're into molten landscapes and apocalyptic weather, that would be a bit of a problem. So if we aren't really keeping any of the sun's energy, what are we actually getting from it? What does the sun really give us? To understand this, we need to first understand how an ideal engine would work. Well, imagine two massive metal bars, one scorching hot and the other ice cold. Between them sits a chamber filled with air, and inside that chamber is a piston connected to a flywheel. If you bring the hot bar into contact with the chamber, the air inside starts absorbing heat and expanding as it does. That expansion pushes the piston upward, which turns the flywheel. Energy is being converted, and then the hot bar is removed, but the air keeps expanding. Without new heat entering, its temperature starts to drop until it cools down to match the cold bar. Now the cold bar touches the chamber. The piston moves back down while compressing the air inside. That compression forces heat into the cold bar. Then you remove the cold bar. The flywheel keeps compressing the air and raising its temperature until it's just shy of the hot bar's temperature. And the cycle repeats. What's happening here essentially is that the heat is flowing from the hot bar to the cold bar. And in the process, some of it gets converted into mechanical work, the turning of the flywheel. And here's where it gets really interesting. This entire process is reversible. You could essentially run the engine in reverse. The air expands first, dropping its temperature. Then it pulls heat from the cold bar. Next, the air compresses, warming up again. The chamber is reconnected to the hot bar, and all the heat goes back where it started. Doesn't matter how many cycles you run forward, you can always run the engine backwards, without any energy loss. So, we've got this perfectly reversible engine. Seems like it should be 100% efficient, right? Well, real life is not very generous. See, with every cycle, the flywheel gains energy equal to the heat taken in from the hot bar minus the heat that gets dumped into the cold bar. In other words, some of that energy escapes no matter what. To figure out efficiency, we take that net gain and divide it by the heat input from the hot side. Now, the heat taken in on the hot side is equal to the work done by the expanding gas on the piston. And because hot gas exerts more pressure than cold gas, the work done during expansion is always greater than the work recovered during compression. If you wanted to make the engine more efficient, you'd have two options. Either crank up the temperature on the hot side or drop the temperature on the cold side. Imagine pushing the cold side to the absolute extreme, so much so that the gas inside the chamber cools to the point where its particles completely stop moving. And if nothing is moving, then there's no pressure pushing back on the piston. That means in theory, you could compress the gas back down without using any work. Hence, no energy is lost. This is the idea of absolute zero, the coldest possible temperature where molecular motion completely stops. And in theory, if you could actually reach this state, you'd have a 100% efficient engine. This idea leads to the creation of the Kelvin temperature scale. And by using this temperature scale, we can simplify things a bit. Instead of tracking the messy details of heat going in and out, we can just use the temperatures of the hot and cold sides. That means we can express efficiency in a simple equation, and after a little rearranging, we get something like this. The efficiency of an ideal heat engine doesn't depend on what it's made of. It doesn't even depend on how it's built. It all comes down to temperature. If you actually wanted to hit 100% efficiency, you'd need either infinite temperature on the hot side or absolute zero on the cold side. And last time I checked, both of those are impossible in the real world. But hitting the subscribe button is not. So even if you eliminate friction, even if there are zero losses to the environment, a heat engine still can't be 100% efficient. And the reason for that is, to reset the piston to its original position, you have to dump heat into the cold side. There's no way around it. That means not all of the energy stays in the flywheel. Some of it has to be lost. So while a perfect engine would put all its energy into the flywheel, a real one bleeds energy everywhere, through the cylinder walls, the axle, and as heat radiating off into the air. Once energy spreads out like that, you can't get it back. That process is irreversible. The total energy stays the same, but it becomes less usable. Think about it this way. Energy is most useful when it's concentrated. The more it spreads out, the less useful it becomes. When German physicist Rudolf Clausius was studying heat engines, he realized that there's a way to measure how spread out energy is. He calls this quantity entropy. When energy is packed into the hot bar, entropy is low. As energy disperses into the environment, the chamber walls, the flywheel axle, and the air, entropy increases. Note that the amount of energy remains the same, it's just not available to do work. Then in 1865, Clausius sums up the two fundamental laws of thermodynamics in a brutally simple way. First, the total energy of the universe is constant, and second, the entropy of the universe always increases. In other words, energy is constantly spreading out. This second law explains so much about the universe. Why do hot things cool down and cool things heat up? Why does gas expand to fill a room? Why perpetual motion machines are impossible? Because in any closed system, the amount of usable energy is always decreasing. Entropy is often described as a disorder, which makes sense. Things tend to break down, mix together, and become less structured. But a better way to think about entropy is it's just energy spreading out over time. But the question is, why does energy spread out over time? Most laws of physics don't care about the direction of time. They work the same forwards or backwards. So where does this clear time dependence come from? Let's break it down. Imagine two small metal bars, one hot and one cold. To keep it simple, let's say each bar has 8 atoms, and these atoms vibrate based on how much energy they have. More energy means more movement. Now, start with 7 energy packets in the hot bar and 3 in the cold bar. These packets jump randomly between atoms, but the total energy stays the same. If we touch the bars together, the energy packets can now jump between both bars. The number of ways this can happen is huge, and each configuration is equally likely, which means 9 packets in the hot bar and only 1 in the cold bar is also possible. But wait, that's heat flowing the wrong way. That's not supposed to happen. Or is it? There are 91,520 ways for 9 packets to end up in the hot bar, but there are 627,264 ways for the energy to spread evenly between both bars. So an even spread is over 6 times more likely than energy staying concentrated in one place. And if you scale this up to 80 atoms per bar and 100 energy packets, the chances of the hot bar getting hotter actually drop to 0.05%. Heat flowing from cold to hot isn't impossible. It's just incredibly unlikely. And a real-world object has trillions of atoms, with even more energy packets bouncing around. The odds of heat randomly flowing from cold to hot become so astronomically small that it just never happens. And even air conditioning doesn't break the laws of thermodynamics. It just works around them by increasing entropy somewhere else. That somewhere else is a power plant. Along the way, heat leaks everywhere, from the wires to the fans to the compressor. So while the air conditioner lowers entropy inside your house, it's causing way more entropy out in the world. But then, why is there structure at all? If entropy is always increasing, and if everything spreads out and decays, then how are there still hot places and cold places? How does life exist at all? Why hasn't the planet turned into a uniform lifeless soup? Well, that would happen if Earth were a closed system. Energy would spread out completely. Everything would decay. life would end and eventually the entire planet would reach a uniform temperature and nothing interesting would ever happen again. But luckily, Earth is not a closed system. The only reason life on Earth hasn't ground to a halt in a sea of useless energy is the sun. Think of it like this. The sun beams down usable concentrated energy, all neat and clumped together in high-energy photons. Everything that was once useful energy is eventually turned into waste heat and radiated into space. It's still the same amount of energy, the only thing that's changed is entropy. You can literally see it in the flow of energy to and from Earth. For every 1 photon the Earth absorbs from the sun, it emits 20 lower energy photons back into space. Without a constant supply of concentrated energy from the sun and a way to dump the leftover spread out energy back into space, life couldn't exist. And the sun gets its low entropy from the universe. The universe started out with low entropy, and it's 15 to 16 orders of magnitude higher today. And because it was low in the past, everything that has ever happened, the formation of stars, the growth of forests, the rise and fall of civilizations, and the evolution of life itself has been possible. And all of it happens in one direction. You never see a shattered glass jump back together, and you never see a melted candle reform its original shape. There is a clear difference between past and future. We are moving from unlikely states to more likely ones. And that is why time has an arrow, why we always move forward and never backward. And this process doesn't stop. It keeps going until eventually energy will be so completely spread out that nothing interesting will ever happen again. This is called the heat death of the universe. In the far, far future, more than 1 Google years from now, that is, a 1 followed by 100 zeros, after even the last black hole has evaporated, the universe will have reached its most probable state. There will be no structure and no usable energy. At that point, even on large scales, you wouldn't be able to tell if time was moving forwards or backwards. Because when entropy reaches its maximum, the arrow of time itself disappears. So high entropy sounds like this inescapable doom, an unstoppable march toward a universe that is cold, empty, and lifeless, the dullest outcome imaginable. But here is the thing, the most interesting things don't happen at the beginning or the end. They happen in the middle. That's where complexity flourishes, where galaxies form, where life emerges, where civilizations rise, and where you and I exist. And that's exactly where we find ourselves right now. And with that, hit the bell icon, stay curious, and I'll see you next time.